Hello and welcome to another video on Hooke's law. And this time we're going to be looking at dynamic systems. So that's when we've got a string or a spring, but the particles involved are moving. So when we do this, we're going to use our Newton's law of forces, mass times acceleration, and possibly friction as well. So we need to bring in all the mechanics we know from year one, further mechanics, and from your single maths mechanics studies as well. So let's have a look at these two questions here. We've got a light elastic string, natural length 0.2, modulus elasticity 6, is attached to a fixed point P. The other end is attached to a particle of mass 0.12 kilograms, and it's held at a point 0.3 meters vertically below P. So it's worth getting your head around what's happening. We've got this situation here. Something is held below the fixed point. So here's the fixed point P. This is held vertically below it. So we've got a force acting down, which is 0.12 G. We're going to have a tension in the string, and we know that this distance here, where it's held when it's initially, is 0.3. So that is how things start off. Let's think what the tension in the string is going to be. Well, the natural length of the string is 0.2. So the extension is 0.3 minus 0.2, which is 0.1. You need to be very clear on what you're using where in these questions. We're going to use tension is lambda x over L. The tension is not equal to the weight here because the system is not in equilibrium. When we let it go, it's going to travel upwards. So let's have a look at the tension. We've got that the tension is equal to lambda, which is 6, the extension, which is 0.1, over the natural length, which is 0.2. And when we work that out, we get 3. So the tension in the string is 3 newtons. So what's the initial acceleration of the particle? Well, we're going to use force equals mass times acceleration, resolving vertically. So we've got the net forces upwards. So we've got T minus 0.12 G is equal to 0.12 multiplied by A. We can put 3 in here. So 3 minus 0.12 G is equal to 0.12 A. And that gives me A is 15.2 meters per second squared. So we found the initial acceleration. Now, part B says, what's the length of the string when the particle reaches its maximum speed? This is something they quite often ask in exams, and there's not many questions in the textbook on this. So it's worth making a special note of how this works. If you imagine the particle stretched right down to here, when you let it go, it's going to accelerate. What's happening to the acceleration as the string returns to its natural length? Well, the acceleration is going to reduce because the tension in the string is going to reduce. When does it reach its maximum speed? Well, it reaches its maximum speed when the acceleration is equal to 0. So maximum speed will be when acceleration equals 0. And the acceleration is equal to 0 at the equilibrium position. So that will be the position if you just let the string rest. That's where you will have the maximum speed because the acceleration at that point will be 0. So we want to set up this system as though it's in equilibrium. So if it's in equilibrium, then what we would have is 0.2 plus the extension here, which we don't know what that is. I'm trying to find that out. We'd have 0.12 G acting down, and this time the tension will be equal to 0.12 G. So we've got the tension is equal to 0.12g, which is 1.176. So then, applying Hooke's law to this, we've got tension is lambda x over L. So 1.176 is lambda, which is 6, x over 0.2. And that gives me x is equal to 0.0392. That's in meters. So the length of the string is going to be 0.239 meters, because that's the extension. And we need to adjust that. Oh, yeah, sorry, there was a long pause there because I was just working out where this had come from. Of course, we're adding 0.2, which is the natural length of the string, plus the extension, which is 0.0392. So that adds to that length of the string. So the important point here is that the maximum speed comes as it comes back through the equilibrium position. That conceptually, that's a little bit tricky, so keep thinking about it and try to remember it when you're in the examination. Right, question 9, we've got quite a lot going on here. So when I'm reading this, I will be thinking about each piece of information I've been given. So we've got a particle mass 0.5 attached to one end of a spring, which is 0.9. And we've got the modulus of elasticity. The other end is attached to a fixed point on a rough plane, which is a slope. And we know that sine theta is 3/5. The coefficient of friction is 0.15. It's held at rest 1 meter down the slope from the point of attachment. It's released from rest and it moves up the slope, find its initial acceleration. So a nice clear diagram showing what's going on. So there's my slope. There's theta. We've got the particle attached here, or the particle here, and it's attached at this point up here. So we've got tension coming up in the string. We've also got the mass giving a weight of 0.5g. We will have a reaction force, a normal reaction force there. And because this is rough and it's about to move, we can put in straight away mu r on our diagram because we know it's going to be moving. It's going to be moving with an acceleration that we've got to find. I would put all this information in a list here so that I was clear on what was what. So I've got the natural length is 0.9. Lambda is 40. Mu is 0.15. And x, the extension, is 0.1 because it's held 1 meter below and its natural length is 0.9. So it's really important that you get the information in the correct order here and the correct values for coefficient of friction and the modulus of elasticity. If you get these wrong at the outset, you're obviously going to get the answer wrong. So it's worth taking some time to make sure everything is where it should be. So at release, what's happening? So at release, we're going to have the tension in the string is lambda x over L. So we can use Hooke's law, and we've got lambda, which is 40. The extension is 0.1, and the natural length is 0.9. So that's 40/9. And I would leave that as that exact value. We're going to need to find R, so we're going to do that by resolving perpendicular to the slope. And when I do that, I'm going to get the R, which we want to find out, is 0.5 g cos theta. And that gives me 0.5 times 9.8 times 0.8 is what cos theta will be equal to. And that gives me 3.92. So I've now got the reaction force, so I can now resolve parallel to the slope. So resolve parallel to the slope and apply Newton's law. So we've got a force of T going up the slope. Down the slope, we've got mu r, and we've got the weight, but we've got to take the resolved component of that, which is 0.5 g sine theta. And all of that is equal to the mass, which is 0.5, times the acceleration, which we're trying to find. It's worth writing this equation because that very clearly sets out your method. And writing the equation in the examination is what gets you the marks, having the equation of motion written out clearly. So now we're going to substitute in the values we know. The tension in the string we know is 40/9. Minus mu is 0.15 times by r, which is 3.92, minus 0.5 times 9.8 times 0.6 is 0.5a. So that gives me, when I work all of that out, a is 1.83 meters per second squared. But the acceleration is going to vary because as the spring returns to its natural length, the tension will reduce. So the force equation here would be different. So this is the initial acceleration, and that's the way this works. So have a go now at exercise 3b, which has some similar questions to these.